Welcome to the demonstration of the green elasticity innovation of the 6Green project. The green elasticity innovation aims to dynamically and adaptively select diverse technologies to enable different trade-offs between performance and consumption, depending on the traffic conditions, availability of computing and network resources, or even of renewable energy sources. One artifact can be more efficient than another. This is why it is very useful to rely on diverse technologies. The main mechanism realizing the green elasticity innovation and presented in this video is the dynamic selection of the user plane function. The proposed prototype involves a common UPF control plane and two data plane offering different performance consumption trade-offs. In this demonstration, we have two data paths configured. The first one is BESS, which is DPDK based, and the second one is the Free5G data path, which is based on a kernel module for packet forwarding. The starting situation is the following. The Free5G data path is currently selected, and since the idle power consumption is almost zero, this data path will be always running even when not selected for packet forwarding. The BESS data path is currently powered off, and it's powered on only when needed due to its higher idle power consumption. As you can see from the graph in the bottom left, there is no traffic, and the power consumption is near zero. The UE from which will generate traffic is already connected, and in the bottom right corner we see the packet capture of both data paths. We now started generating traffic from the UE using the iPerf3 tool. We'll start with the bandwidth limited to 200 megabits per second, and we'll increase it gradually. As you can see from the graph, the power consumption of the data path increased due to the generated traffic. We'll now run iPerf with a bandwidth limit of 500 megabits per second. We now increase the bandwidth to 750 megabits per second. As you can see, the power consumption increases at every step. For the final test on this data path, we'll disable the bandwidth limit so that we can see the maximum that this implementation can handle on our hardware, which, as shown by the terminal and the graph, is a bit more than 1 gigabit per second. We also disable the time limit to keep it running while we test the data path switching. On the UPF switching interface in the top left, you can also see a graphical representation of packets flowing to the currently selected data path. We now initiate the switch to the best data path. This will take a bit of time because it first needs to be powered on. To prevent service disruption during the switching procedure, the traffic continue to flow on the old data path until the selected one is ready. The switch was successful, and the traffic is now handled by the BESS data path. The switch didn't interrupt the running bandwidth test since it's completely transparent to UE and the applications running on it. Even existing TCP connections would not be interrupted. With this data path, we now see that the bandwidth has increased to more than 2 gigabits per second. We are now going to do more bandwidth tests, decreasing it each time. The first one is at 1 gigabit per second. Now we are testing at 750 megabits per second. Now we are testing at 500 megabits per second. The last test is going to be at 200 megabits per second. Looking at the graph, we can see that the BESS data path is much more efficient when the bandwidth is really high. It can deliver double the speed of the free 5G data path with little more power. But as the speed goes down, we see that the power consumed is always more than free 5G, and more importantly, in the time between the tests when the bandwidth is zero, it keeps consuming energy. This is even more visible at the end when no test is running. We are now going to switch back to the free 5G data path. This will automatically power off BESS. We'll be able to see that in the graph where the power consumption is going to zero.